Now let me explain the excitation phase of cardiac myocytes. For that, I have drawn two different graphs to show the difference between normal nerve impulse propagations or action potential of nerve cells and action potential of cardiac muscles. This graph represents the action potential of nerve cells or neurons, and this graph represents the action potential of myocytes, cardiac myocytes. Okay. Now, one thing I have to mention that here I have drawn this graph with different color because these are different phases. This is called resting membrane potential that I have mentioned previously at minus 70 millivolt. Okay. Now this red graph represents the depolarization phase of the action potential. The blue represents here the repolarization phase of the action potential, and this short phase that actually goes down of the resting membrane potential called hyperpolarization. And as because you can see here is a gap between the first action potential and second action potential. Always there is a gap, there is a period between this first and second or consequent action potential. This is called refractory period. Refractory period. Now the x-axis represents the seconds, the time in millisecond, and this axis represents the membrane potential in millivolt. Now in case of nerve cells, action potential of nerve cells, the duration of this depolarization and repolarization is only about 1 to 2 milliseconds. This is very interesting. In case of mammalian nerves, it takes just 1 to 2 milliseconds for the whole action potential to occur. In case of myelinated nerves, it takes less than 1 milliseconds. So the duration of this total action potential is very short. That's why it is called spike. Action potential is also called, in case of neurons, spike. Okay. And during each action potential, there is a refractory period, and the refractory period is about 4 milliseconds. So the refractory period is more than the action potential. R means resting membrane potential. Resting membrane potential. Now this resting membrane potential is actually maintained or actually established by two proteins, transporter proteins I have mentioned already, that is sodium and potassium pump, and another protein is called potassium leaky channel. Leaky channel. Also, this potassium leaky channel is called potassium inward rectifier. You can remember the name potassium. I'm writing here potassium inward rectifier. This leaky channels are also called KIR channels. So these two transporter proteins establish the resting membrane potential that is about minus 70 millivolt. Okay. And in this resting membrane potential, the inside of the cell remains negatively charged than outside, and outside remains actually positively charged in all animal cells. Okay, not for neurons, for all animal cells. Now these depolarizations, D for depolarizations, occur due to the presence of voltage gated sodium channels. So I am writing here NAV, that means voltage gated sodium channels. And why it is called depolarization? Because here the membrane potential becomes positive. That means the inside of the cells become positively charged and outside become negatively charged. Reverse occur. So in case of resting membrane potential, outside is positive, inside is negative. In case of depolarizations, the reverse occur. Outside will become the negative charge and inside become positive charge. This is called depolarization. Sodium channels, voltage gated sodium channels are important. Now these repolarizations occur. Repolarization occur due to potassium channels. Now this potassium channels is different from this leaky potassium channels or KIR because they are called delayed, as because they open, this potassium channels opens after a few milliseconds. That's why it's called potassium channel, delayed potassium channel. So repolarization, during this repolarization, what happens actually, this positive membrane potential becomes again negative membrane potential. It actually comes down. Now what happens in during these repolarizations, the volt membrane potentials becomes more negative than the resting membrane potentials, that means minus 70 millivolt. Repolarization means this positive membrane potential becomes negative membrane potentials, negative value. And now another thing occurs, that is called hyperpolarizations. I have right here in black color, hyperpolarizations. And what happens here, this value of this membrane potential becomes less than minus 70 millivolt. That's why it is called hyperpolarizations. And this hyperpolarization also occurs due to the potassium channels, that is delayed potassium channels. And ultimately, when these all things occurs, that means depolarization, repolarization, hyperpolarization occur, then after some refractory period, in this refractory period, this sodium potassium pump and potassium leakage channels then actually re-establish the sodium potassium concentration gradient and the membrane potential to this minus 70 millivolt. That's why it actually continues to generate the action potential. Now let me explain the cardiac myocytes. Here only the action potential takes 1 to 2 milliseconds, and in case of myelinated neurons it takes less than 1 milliseconds. But in case of cardiac myocytes, here is the difference. The main first difference is the duration of the action potential is long, more than the this neuron action potential. The duration could be up to 200 milliseconds. See the difference between action potential of neurons and action potential of cardiac myocytes. It can last for 200 milliseconds. Now why this long lasting action potential is required for cardiac myocytes? The requirement is because of the intracellular calcium movement, transport of intracellular calcium, and the contraction. Now intracellular calcium means in the cardiac myocytes or in any muscle cells, there is a special organelles that is very similar to the endoplasmic reticulum of other cells called sarcoplasmic reticulum. Sarcoplasmic reticulum, in short we call SR. So from this sarcoplasmic reticulum in muscles like cardiac muscles also, the calcium is stored, and from this intracellular store or organelles, the calcium is released, and during this long time period, it requires this long time period to release the calcium and cause the contractions. Now here also I have drawn different color. See this is the basically in cardiac myocytes, the action potential is represented with different phases. So there are 4 phases. Okay, the phase, this is the phase 0, this is the phase 1, this is the phase 2, phase 3, and phase 4. This is also the phase 4. Now let me write here. This green, the phase 4 represents the resting membrane potential. Resting membrane potential. In case of cardiac myocytes also, the sodium potassium pump and potassium leakage, and that means KIR, the sodium potassium pump and the inward rectified potassium channels or leaky potassium channels actually maintain the resting membrane potential. In all animal cells, this is the cause of resting membrane potentials, and in this case the resting membrane potential is below the minus 90 millivolt, because in my previous video I have also mentioned that the resting membrane potential is not fixed at minus 70. It could vary from minus 20 to 200, minus 200 millivolt. It depends on the cells and organisms. So it is below the minus 90 millivolt, and it is maintained by this sodium potassium pump and the leaky channels. The 0, that means this phase, the phase 1, I'm writing with red color. Phase 0 is actually called the rapid upstroke or rapid depolarization. So basically this is the depolarization. As I have mentioned, depolarization means from the resting membrane potential, that is negative membrane potential, it becomes positive. That's why it is called depolarization. So rapid upstroke or rapid depolarization occur. Now for this depolarizations also voltage gated sodium channels are important. Voltage gated sodium channel is important. In this case, this is called sodium voltage gated sodium channel 1. 1 means here the subfamily represent 1 in cardiac myocytes. Now in the phase 1, this is called depolarization notch or early repolarization. Why it is called depolarization notch or early repolarization? Because as you can see, from less than minus 90 millivolt, the upstroke, rapid upstroke or rapid depolarizations actually goes up to positive 30, and here it stops. In these short periods or short phases, this in phase 1, the depolarization actually stops. That's why depolarization notch or early depolarization starts. The first is potassium channel, voltage gated potassium channel is 4.3. Now here the first is called subfamily like this, and this is the isoform. So 4 is subfamily. So voltage gated potassium channel subfamily 4, and 3 is the isoform, specifically for cardiac myocytes. Okay, and another channels are responsible, that is called voltage gated calcium channel. Voltage gated calcium channel, that is 1.2, that means subfamily of 1 and 2 isoform. These two channels are important for phase 1. Now I want to also mention that remember these calcium channels present in the plasma membrane of cardiac myocytes, and these channels actually cause the influx of calcium into the cell. Okay, now the phase 2, also it is in red. So phase 2 is called plateau phase, repolarization or depolarization plateau phase. So depolarization plateau phase. Now as you can see, this is the 0 millivolt, and at these positions the action potential stays. So this phase remains, actually maintains the depolarization. This is called depolarization plateau. Now from 0 millivolt, and when this action potential or membrane potential falls below the 0 millivolt, we call phase 3. So yes, it is blue in color. So phase 3. And this phase 3 is called repolarizations, just like these repolarizations. So see here, there is no difference, major difference in the action potentials. There is resting membrane potential, depolarization, repolarization. As you can see, resting membrane potential, depolarizations, and also repolarizations occur. But in between that, there is a depolarization notch, and this depolarization plateau that maintains the longer duration of the action potential of cardiac myocytes. Okay, so phase 3 means repolarization. The same occurs here also. The potassium channels, that is delayed potassium channels, voltage gated, obviously these are all voltage gated. So voltage gated potassium channels here in this cardiac myocytes, specifically 7.1 and voltage gated potassium channel 11.1, they actually perform these repolarizations also with the help of this inward rectifier potassium channels. Okay, so there is similarity, and after that it actually go to the 4, that means the resting membrane. So there is a 4 phases of the action potentials occurs. Now the main important point I want to mention here, that this calcium channels opens, and that causes a small influx. Remember, small influx of calciums. Now this is the first phase of the excitation-contraction coupling. That means here the action potential actually generated. Now during this action potential, contraction will occur and simultaneously relaxation will occur. So I will also explain how this contraction phase occurs in the cardiac myocytes, then we will understand the sodium calcium antiporter. Now let me explain these cardiac myocyte action potentials through this diagram. It will help you to understand more. So as you can see, this is the action potential of cardiac myocytes. There are 5 different phases of action potential occurs from 0 to 4, and this is a cyclical form. So at first I will explain resting membrane potentials. As I have mentioned, resting membrane potential is maintained by sodium potassium pump and potassium inward rectifier or leaky potassium channels. So this is the resting membrane potential, and when action potentials arrive, then suddenly voltage gated sodium channels actually opens. This voltage gated sodium channel is opened and rapid depolarization or rapid upstroke occurs. That means from minus 90 millivolt it goes up to plus 30 or up to more than millivolt. So why it occurs? Because the opening of voltage gated sodium channels and sodium influx occur. Sodium actually comes inside the cell, and the membrane potential reversal occurs. As you can see, outside was positively charged, now outside was negatively charged. But in case of cardiac myocytes, here is the difference, because suddenly there is a rapid or you can say early depolarization occurs, that is called depolarization notch. Here it breaks. The depolarization does not continue up to this mark. It actually stops here. As you can see, it stops here. That's why it's called depolarization notch or early depolarizations. Now what happens here, one voltage gated potassium channel is actually open, and it efflux the potassium channels from inside to the outside, and that causes the reversal of the membrane potential. So it falls, shortly falls, but it is counterbalanced by a calcium voltage gated calcium channels called voltage gated calcium channel 1.2. It causes the full-blown repolarization as occurs in the nerve cells. Okay, if these calcium channels are not open, then repolarization can occur, but obviously this potassium channel is transiently open. Okay, now in the plateau phase, this phase is important because here, from here, it actually maintains the depolarizations. Now depolarization is maintained because of the influx of calcium from these calcium channels. Remember this, the calcium that enters through the calcium channel is small in amount. The major calcium influx occur through the sarcoplasmic reticulum from the cytosol. So this calcium actually causes the small influx, but this calcium influx actually maintains the depolarization state, because here counterbalance is performed by the delayed potassium channel. So there is a inward movement of positive ions and outward movement of positive ions that causes the delay or longer duration of the action potential in case of cardiac myocytes. And after that, repolarization starts to occur. Here both the delayed potassium channels and the KIR removes the more positive ions. Now let me talk about the contraction phase of cardiac myocytes. So I will draw the plasma membrane, and let's suppose this is the exterior of the cardiac myocytes. This is the exterior, and this is the cytosol of the cardiac myocytes. So in the plasma membrane, there is a calcium channels. There is calcium channels present. That is, I have mentioned calcium channel, voltage gated calcium channel 1.2 in the plasma membrane. In the phase 1 and also the phase 2, I forgot to mention that here also voltage gated calcium channel and this delayed potassium channels, these two channels actually works. Okay, so during this phase, that means during the plateau phase and also during the depolarization notch, so this first and second phase, the voltage gated calcium channels are opened, and through this calciums actually move inside. Calcium moves inside. Now, as I have mentioned, that in all cells, the concentration of calcium in the outside remains high, and inside the cytosol remains low. So when calcium moves from higher, here concentration is higher, to lower concentrations, it means it is following the downhill movement. So it is easy to move higher concentration calcium to the lower concentrations. So this is the first step occurs in the contraction phase. Remember this that the amount of calcium that enters, that is small in amount, not in large amount. Small amount of calcium actually enters. Now this entry of calcium causes one important phenomena that is called calcium induced calcium release. So a small influx of calcium through this voltage gated calcium channels during this phase 1 and phase 2, that means depletion notch and depletion plateau phase in the cardiac myocytes, small amount of calcium causes calcium induced calcium release. How it occurs? Basically in all muscle cells like cardiac muscles or skeletal muscles, there is a intracellular organelle called sarcoplasmic reticulum, as I have mentioned here. This intracellular organelles actually store calcium. Here the concentration of calcium is just like the concentration in the outside, that is 10 to the minus 3 millimolar. So more calcium actually stored inside the sarcoendoplasmic reticulum. Now in this sarcoendoplasmic reticulum of SR, sarcoplasmic reticulum, there is a channel called, I'm drawing here, there is a channel called ryanodine receptor 2. In case of heart muscles, the 2 isoform is present. In case of skeletal muscles, ryanodine receptor 1 actually present. This channel, basically this is a calcium channel. This is a calcium channel. Why it is called ryanodine? Because one plant alkaloids, ryanodine, can bind in these channels and it can block the channel. That's why it's called ryanodine receptor, and this receptor is 2 in isoform in case of heart muscles. So this is actually calcium channels. This calcium that influx through these calcium channels that present in the plasma membrane. Now this calcium binds with these channels and causes the efflux of calcium from the SR to the cytosol, and this amount of calcium is huge. So that's why it's called calcium induced calcium release. Calcium binds with the ryanodine receptor calcium channels and then it actually efflux more calcium, so its amount is huge. So huge amount of calcium are released. Okay, now for this release of calcium, what happens? Contraction occur. Here the protein called, that is calcium sensitive, called troponin C, that means the calcium sensitive protein actually cause the contraction of myofilaments. That's how the contraction of heart muscles occur. Now this is the contraction phase. Now there must be a relaxation phase also. For the relaxation, this sodium calcium antiporter actually plays that role. As you can see, as much as calcium enters through this channel, that amount of calcium actually are extruded. Extrusion occur, that means efflux occur of calcium through this sodium calcium antiporter. So through this sodium calcium antiporter, the amount of calcium that enters through the channels, these channels are actually removed. So not more amount of calcium are removed through these channels, small amount of calcium is actually removed. But here in the sarcoplasmic reticulum, here is a ATPase pump is present, calcium pump present, that actually causes the influx of calcium from the cytosol to the sarcoplasmic reticulum. So by lowering the calcium amount by the two mechanisms, one is present in the plasma membrane, the sodium calcium antiporter, and the calcium pump. Calcium pump means here ATP breakdown occurred to move the calcium from lower to higher concentrations. Okay, calcium remains low because there is a 10,000-fold difference in between this outside and this SR concentrations. So in this phase, what happens? This sodium and calcium antiporter, through this antiporter, calcium actually moves down. How much moves? Small amount that are moved by these channels. And here through this calcium pump, huge amount of calcium actually are get inside the SR, because huge amount of calcium actually secreted out through this SR. So that's how this actually maintains the excitation contraction coupling. So I think you have understood where the sodium calcium antiporter stands. So there is the action potential, there is phase 1 and phase 2 where this calcium influx starts to occur. This is the plateau phase, and after that, during this phase, the contraction actually occurs, and after these repolarizations, from these repolarizations, basically calcium influx starts and the muscles become relaxed. That's why it actually goes to the resting membrane potentials. So during these repolarizations, small amount of calcium released through this antiporter and a huge amount of calcium are actually entered inside the sarcoplasmic reticulum. Now the last thing I want to mention, that this sodium calcium antiporter can work in two modes. One is forward mode, another is reverse mode. Now what is the forward and reverse mode? Let me explain. Suppose this is the plasma membrane and this is the sodium calcium antiporter. In normal conditions, normal situations, what I have mentioned, that sodium that is present in the exterior will move inside. This is the cytosol, and calcium will move out of the cell, and that's why it causes the relaxations. It causes the relaxation of the cardiac muscle. Okay, this is the forward mode of the antiporter. But in the situations of this, during this action potential, this blue line is the action potential of the cardiac myocytes, sometimes this antiporter works in reverse mode also. What is reverse mode? The opposite will occur. Sodium efflux occur, sodium will come out and calcium moves in. So the opposite can also performed in these action potentials. Here remember, in these situations actually muscle contraction occur. So basically this antiporter not only helps in the relaxation but also during the contractions, because it contributes the calcium to the cell. How it occurs? One thing we have to understand for this blue line represents the action potential of the cardiac myocytes, and this black line represents one important point. We call it equilibrium potential. Equilibrium potential of sodium calcium. We call this antiporter, or we can also say it is exchanger. Antiporter, we can also say this is exchanger. So in short, we call NCX. This black line denotes the equilibrium potential of this antiporter or exchanger, NCX. In short, we call it ENCX. Now what it means? It means at this membrane potential minus 30 millivolt, this antiporter will not work. It will stop its working. Now this is the membrane potential. This represents the membrane potential. In short, we call EM, membrane potentials. Now when the membrane potential, remember this, membrane potential is less than the equilibrium potential of this exchanger, then forward movements occur. When forward movements occur in this time period, remember this, in this time period, that means the third phase. This is the third phase. Remember this. During this third phase, that means during the repolarization phase, here, as you can see, it is less than 30. So from here, less than 30 millivolt, minus 30 millivolt, that means the membrane potential is less than the equilibrium potential of the exchanger. So in this durations, the antiporter will work in forward movement. That means during it actually causes the relaxations, because this is the repolarization phase. But as you can see, this phase, in this phase, in this phase, here the membrane potential is actually more than the equilibrium potential of this exchanger, and that's why it is reverse in mode. So the movement of ions basically depends on the equilibrium potential of this exchanger. If the membrane potential is less than equilibrium potential, that means less than -30, then in this phase, in this time period, it will work in forward mode. But during this period, when the membrane potential is up than the 30 millivolt, this same antiporter will work in reverse mode and will enter calcium for the contraction of the heart muscles. This is the whole story of sodium calcium antiporter. Hope this video will help you. Thank you for watching and always keep learning.